All right. Okay, upper bounds on the b-chromatic number. So first of all, we know that all the colors except its own need to appear in the neighborhood of a b-vertex. So this implies that we can have at most the maximum degree plus 1 colors in any b-coloring. Right? I mean, in this case, maximum degree is 2, so we cannot have a b-coloring with 4 colors, right? Because a b-vertex needs to see 3 colors in the neighborhood.
How do I know that b-coloring exists at all?
Sure, it does exist. Or I don't.
Yes, you have to have a coloring where every color appears. You have to color.
Yeah, I mean, for example, if you look at a bunch of stars that have a given number of leaves, then you can give the center any color, and the leaves you color in all the other colors. So then for any integer, you can create an example like this. Right.
So the maximum number of colors, where you have a b coloring.
Yes, yes.
So I want to know whether I have at least one b coloring.
So you just take a heuristic and continue to pass.
Yeah, for example, or that. Yes, yes, yes. I mean, if you apply this heuristic, you always end up with a b coloring, because otherwise you would proceed. Right. Yes, yes.
Otherwise it merge.
Yeah, otherwise you just keep suppressing colors. Yeah, yeah. And then you have fewer and fewer colors. Yeah. Okay, so this upper bound only looks at one b vertex at a time. But I mean, of course, we need a bunch of them, right? We need k b vertices for a b coloring. And this is what this so-called m degree describes. So m of g is the maximum integer I, such that g has I vertices of degree at least I minus 1. So this is precisely saying that the m degree describes like the maximum number of colors in any b coloring of the graph, because you need these vertices that see all the other colors. Right? Okay, so this is the second upper bound. It's just that the b-chromatic number is upper bounded by m of g. Okay, so formally we are considering this problem. We are given a graph G and an integer k, and the question is, does G have a b coloring with k colors? Now I'm stating some results that are important for the motivation of this work, but there are many others. So we know that if we look at any value of k, and here by general k, I mean it's not related to one of these upper bounds that we're considering, then it's known to be NP-complete when k is unbounded. So that's probably not so surprising. And the problem remains NP-complete if we restrict the question to, does my graph have a b coloring with delta of g plus 1 colors, or does my graph have a b coloring with m of g colors? So if we want to know if a graph achieves this upper bound, this question is also NP-complete. Right, and then if we look at small values of k, so if k is bounded, then for general k, this problem remains NP-complete for any fixed integer k. But if we want to answer the question whether our graph has a b coloring with maximum degree plus 1 colors, then we can do this in f of k plus some poly of n time. And now let's look at this result. What does this mean intuitively? In some sense, it means that for small k, we can recognize the hardest instances for the heuristic efficiently. Right, but this, of course, only holds if we want to know whether our graph exactly achieves this upper bound. So one of the main questions of this work was, what happens if the requested number of colors is only close to one of the upper bounds, like maybe 1 or 2, 3 below? What happens then? Okay, and this is the first main theorem. So suppose we have some graph, some integer p, which will measure the distance to one of these upper bounds, and some integer that is either the maximum degree plus 1 minus p or m of g minus p. Then we have that the problem of deciding whether G has a B coloring with K colors is NP complete if K is unbounded and P is either 0 or 1. It remains NP complete even if K is 3 and P is at least 2. And finally, we carve out this small area of tractability, namely we show that it's polynomial-time solvable if K is bounded and P is either 0 or 1. So if we want to know if our graph either achieves the upper bound or it's 1 below, then we can do it in polynomial time for small k. Otherwise it's hard. Okay, then the second result that we have in this work is the following. Okay, so if m of g is small, then we know that the number of high degree vertices is small. Right, but it gives a very precise bound on the number of high degree vertices. So to be a little more flexible, let us just consider this parameter Lk of g as the number of vertices of degree at least k in the graph.
Can you remind the definition of M?
So m of g is the maximum integer I, such that we have at least I vertices of degree I minus 1.
Like the H index.
Oh.
Yeah. Yes.
At least I minus 1 or degree exactly I minus 1?
At least. So it just guarantees potentially the existence of the B vertices for I colors. Yeah. Okay, so if we look at this Lk, then we have that B coloring is NP complete when Lk is unbounded, and we are only looking for a 3B coloring of a graph with maximum degree 4. So, yeah. And then furthermore, if Lk is 0, but the degree is unbounded, then the problem is also NP complete. This is just a reformulation of some of the results on the previous slide. So what we consider is the case when both of these quantities are small, and we show that we can test in time some function of the maximum degree and L plus polynomial in n whether a graph has a B coloring with K colors. Okay. So now I will briefly touch on the hardness results and prove the first item of theorem 1. So here is again the statement. We have some graph G, P is either 0 or 1, and K is the maximum degree plus 1 minus P or M of G minus P. Then the problem of deciding whether G has a B coloring with K colors is NP complete. So there are several proofs for the case P equals to 0, and there's this one proof by Habe et al., and they show a reduction from 3 edge coloring on 3 regular graphs. And I'm not going to show the details, but so we basically just adapt their reduction and also manage to prove the case P equals 1. And yeah. So the second part of theorem 1 is that, so this is slightly reformulated, but it says essentially the same thing. It says that for any fixed integer P, it's NP complete to decide whether a graph G has a B coloring with 3 colors when delta of G is P plus 2 or M of G is P plus 3. Okay, and this works as follows. So there is a reduction from 3 coloring on 4 regular graphs to, for the case P equals 2. So P equals 2 means we want to know, is there a B coloring with 3 colors in a graph of maximum degree 4? Right? And the reduction is very simple. So we just take the same graph and we add 3 stars. And these stars can serve as the B vertices in any B coloring of the graph. So if G has a proper coloring, then we can just color these 3 stars accordingly to make it a B coloring. And otherwise, of course, if we have a B coloring of the graph from the reduction, then we also have a 3 coloring in the original graph. And then if we look at these stars, we can just add a few more of them or increase their degree to make the reduction work for any fixed P. So,
Sorry, I didn't catch it. What is the role of the 3 stars?
yeah, maybe I can just draw something. So we have our graph G, right, and then we add these 3 stars. And now, suppose we have a 3 coloring in G, right, then we can just give this vertex color 1, here 2 and 3, this vertex color 2, this 1 and 3, this color 3, and this 1 and 2. And then we have a B coloring of this graph, right? And I mean, for the other direction, we always know that we can color the stars with 2 colors. So if we have a B coloring of this graph, then we also have a proper 3 coloring of the original graph, right? Because we just forget about these guys.
Isn't it a little artificial to have these disconnected graphs? I mean, when I'm doing this heuristic, I'm trying to color my graph. I'm not going to worry about different components. I color each component individually and don't think about what the other components
Sure. Well, but I mean, this is an entirely different question. I mean, this is just a hardness proof. And if you look at the reductions in many hardness proofs, you might ask the same question, but it's, yeah. Maybe there's a nicer one that does something. Okay. Anyway, then let's talk about the algorithms of the dichotomy result. So let me repeat the statement. So suppose we have some graph G, P is either 0 or 1, and K is again within this range, and K is fixed. Then there's a polynomial-time algorithm that decides whether G has a B coloring K colors. So first of all, we have seen in the beginning that the case of delta of G plus 1 is already known. Right, so this was this result that it's solvable in f of k plus some poly n time. So what we do is that we give algorithms for the remaining cases. And note that these algorithms will run in time n to the f of k as opposed to f of k plus n to the O of 1. Which is, from the perspective of parameterized complexity, much worse. But still, if k is fixed, then this will be polynomial. Okay, so to give these algorithms, we just introduced this notion of a B pre-coloring, which is essentially a pre-coloring of some of the vertices of the graph that induce a B coloring. So what does this mean? So if we look at this coloring, we have these 4 colors and we have 1 vertex for each color that is a B vertex. Right, and we know that the whole graph has a B coloring if and only if there is a B pre-coloring that can be extended to the remainder of the graph. Right. And yes, and then it is not so difficult to argue that the number of such B pre-colorings is bounded by roughly n to the k squared. Right, I mean, first we have n to the k choices for the sets of B vertices. Then for each B vertex, we have to consider a subset of k minus 1 neighbors. That makes this a B vertex. And then we have to consider all the combinations of these k minus 1 subsets. And then again, for each subset, we have k minus 1 factorial different colorings. And again, we have to consider all the combinations. So, yeah. And we can also enumerate them within more or less the same time bound. All right, let's look.
When you are pre-coloring
sorry.
subset, a pair of subgraph and subcolor.
No, it's just a pre-coloring of the vertices that satisfies. No, just a subset of the vertices. But there's a good, I forgot to talk about one point. What does minimal mean? So minimal means that we don't have any unnecessary vertices. So in this pre-coloring, we do have one, at least, unnecessary vertex, namely this one. Right? So this guy is the B vertex for the color yellow, but it also has another vertex that has this color. So we could just remove this one and we still have a B pre-coloring. So it's just a B pre-coloring such that no subset of the vertices. Yeah. Okay, so the first algorithm is for the case k equals m of g. And then we just partition the vertex set of the graph into two parts. First, the ones with degree at least k, and then the ones with degree less than k. By the definition of m of g, we know that the size of d is at most k. Right, because if we had k plus 1 vertices of degree at least k, then m of g would be k plus 1, and not k. Okay, so what do? Well, we enumerate all the B pre-colorings and all the colorings of D. And then we see that the vertices that have not yet received a color are of degree less than k. And this means that any proper coloring of this graph can be extended to the rest of the graph. Right, because if we have a vertex and we have strictly less than k neighbors of this vertex, then we know that there's always at least one color available that we can assign to this vertex.
With color D, you want them to be D vertices.
Yes.
By selecting neighbors in a certain way.
Yeah. Okay. And by the lemma before, we have that there's at most n to the O of k squared pre-colorings that we have to consider, and then the pre-colorings of D are k to the k. So, and as I said, any such pre-coloring can be extended greedily. So this is good enough for us for now. Okay, and then the second algorithm for the case k equals delta of g uses the following theorem that says that given a graph whose maximum degree is at most k and some pre-coloring of any vertex set, we can decide in polynomial time whether this pre-coloring can be extended to the rest of the graph. So note that this is not necessarily immediate because, some things might go wrong. But then what do? Again, we just enumerate all the B pre-colorings and we use this algorithm to check if it can be extended to the remainder of G. And that's all we have to do. And then finally, for the case k equals m of g minus 1, we have to do one small trick. So we just show that we can use the previous algorithm to solve a slightly more general case, which is that not the maximum degree of G is bounded by k, but rather the maximum degree of any vertex that has not yet received a color. If you think about this for a few moments, then it makes sense that if you can do the one, you can do the other. Now we are in the following situation. This looks very similar to the first case. So now here D is the set of vertices of degree strictly greater than K. Here we have the vertices of degree at most K. And again, we know that the size of D is bounded by K plus 1 by the definition of M of G. So we enumerate all these colorings, and then we apply the algorithm of this lemma, which runs in polynomial time. So again, we're happy. Okay, so now I will spend some time with this algorithm. And okay, so the previous algorithms all run in time n to the f of k for some function f. Now in the field of parameterized complexity, we want to distinguish running times of the shape some function of k times some fixed polynomial against running times of like n to the g of k. And it is clear that as k is growing, these FPT algorithms are much, much better than these XP algorithms. And there are actually some nice tables that show the difference or the ratio between typical FPT and XP algorithm, and they're, even for small values of n and k, already quite big. All right, so, okay. So recall that Lk of G is the number of vertices of degree at least k in G. Now what we will prove is the following. So we prove that there is an algorithm that decides whether G has a B coloring with k colors in time f of delta. Whoops, this has to be L. I'm sorry. Yeah, this is L. Plus some polynomial in N. And if there is such a coloring, it also constructs one. Okay, so first of all, we apply the following reduction rule. Suppose we have a vertex V that has degree strictly less than k minus 1. Also, all its neighbors have degree strictly less than k minus 1. Then we know that neither V nor any of its neighbors can be a B vertex. We also know that if we have a proper coloring of G minus V, then we can extend it to a proper coloring of G, because there's always some color available. So this means that we can simply remove this vertex V. And I will tell you in a bit why this is helpful. So let's look at our graph and partition the vertex set of the graph into 3 parts. First, we have the vertices of degree at least k. This is the set D. The set T is the set of vertices of degree exactly k minus 1. And R, the rest, these are the vertices of degree strictly less than k minus 1. So, because we applied this reduction rule, we know that every vertex in R has at least one neighbor in D union T. Right? Because if not, then we can remove it. Okay, so the algorithm now works as follows. We pick some set of vertices B that is maximal, but note that we don't guess this set. We really just pick any maximal set B with a property that all vertices in B are pairwise far apart. And far apart in this case means a distance at least L plus 2. Okay, and note that this set of vertices is chosen from the set of vertices in G that can be B vertices. Right? Any B vertex of the graph has to come from this set, because in R the degree is too small. Okay. Now what we do is we do a case analysis based on the size of the intersection of B with T. Okay. And then we show that if the size of this intersection is small, then our graph is actually small. Where in this case small means the number of vertices is bounded by a function of the maximum degree and L. And if the size is large, then we will show that we can actually construct a b-coloring of G in any case. Okay. So now let's look at the first case. Say that the size of the intersection of B and T is strictly less than K. And so for each I, this should be L plus 1. Suppose that, so let Si just be the set of vertices in G without B union D that are at distance precisely I from B. Okay? Then we can first observe that any vertex in T union R is at distance at most L plus 2 from B. And why is that? Well, in the beginning we have argued that, okay, so first of all, we know that we don't have a vertex in D union T that is at distance L plus 2 or more. This is because we chose our set B to be inclusion-wise maximal. And then in the beginning we also argued that every vertex in R has at least one neighbor in D union T. So this means that the maximum distance of any vertex in R from B is L plus 2. Okay, so we know that that this is actually a partition of the entire vertex set of the graph. Okay, now let's look at this partition. We know that this set has size at most K plus L. Actually, strictly less. Because we know that the intersection of B with T is less than K, and we know that the size of D is at most L. So this is this found. Then we also know that the size of S1 is at most L times the maximum degree, because these we have at most L vertices with degree more than K, and then the remaining K vertices can have a degree only K minus 1 or less, so this is an upper bound on the size of S1. Then we also know that every vertex in these sets has degree at most K minus 1. This means that if we look at some set Si, then we know that there are at most K minus 1 times number of elements in Si minus 1 many vertices. Okay? And this means that this is just the size of S1 times K minus 1 to the I minus 1. Okay. Furthermore, we know that K minus 1 is at most the minimum of L and delta. This is because of an argument I skipped in the beginning. But it's not a strong assumption. Anyway, so now we can derive that if we just scramble the numbers that I showed you on the previous slide, that the size of V is actually O of L times delta times the minimum of L and delta to the L plus 1. And this is small for our purposes, right? Because the size of G only depends on L and delta. Okay, so in this case we can just use a known algorithm that solves the b-coloring problem in time 2 to the O of all of this. Okay, now let's consider the second case when we have at least K elements in the intersection of B with T. So first what we do is we pick some K vertices of this set, and let's just call them x1 to xk. Then we compute any proper coloring of the graph, the subgraph of G induced by D and these vertices that we picked. Okay. And now what we do is the following. So if this coloring gamma does not satisfy the following condition, then we will show that we can modify gamma to satisfy the following condition. And this condition is that either every vertex xi can be a b vertex for color I, or we can find a B vertex for color I in this set D. Okay, so first of all, we will prove one small claim. So for I not equal to j, we have that xi and xj are in different connected components of this graph. Okay, and why is that? Well, suppose not. Suppose we have some path connecting x1 and x3. Then we know that the number of internal vertices on that path is at most L. Right, but then this means that the distance between these two guys is at most L plus 1, and that's a contradiction with a choice of B. Okay, so now let Ci be the component of the subgraph of G that contains Xi. So now we know that if we look at some of this component, we can recolor some of its vertices without creating a conflict in any Cj for j not equal to I. And this also means that we can assume that the color of Xi is actually I. Because if not, we can just swap the color I with the color of Xi, and this doesn't create a conflict with the remaining graph. Okay, so now we observe the following. Suppose we have a vertex like this, and the vertex is colored red. Then we have that if the coloring is injective on its neighborhood, then we are happy. And why is that? Well, we know that all the pre-colored vertices have different colors. So then if this guy has some neighbors in here, we can just assign them the remaining colors and make x1 a B vertex for color red. Right, so this means that the bad situation is that if two vertices in the neighborhood of x1 have the same color. But this also means that there is some color that does not appear in the neighborhood of x1, and in this case, suppose it's green. Okay, now what we want to do is we want to get rid of the color green in all of this component. Now suppose we have a vertex that is colored green such that all the other colors appear in the neighborhood of that vertex. But that's one of the good situations, right? Because that is the case when we found another B vertex for a different color, in this case green. But again, we can just swap colors green and red, and we will have a B vertex for color red. Okay, but then suppose that there is some color that does not appear in the neighborhood of this vertex. Well, then we can just recolor it to something else. And this means that we can just repeat this process such that either we found a B vertex for color red, or we just removed one color from this component, and in that case we can just recolor one of the neighbors to the missing color, and we can continue this process. Okay, and it's not difficult to see that this only takes time polynomial in L. Okay. Right. Okay, so then we have found this pre-coloring, and like I said in the beginning, if one of these vertices does not have all the colors in the neighborhood yet, then there are some remaining vertices that have not yet been colored, and yeah, we just assign them accordingly. Furthermore, all the vertices that have not received a color yet in the remaining graph are of degree at most k minus 1, so we can just extend the coloring greedily. Okay, and this proves our theorem. Okay. Right, so conclusion. So first we have shown this complexity dichotomy for the b-coloring problem with respect to these two upper bounds that we talked about, and most of the things are hard except these two cases when we are asking precisely for the upper bound or one less, and the value, the number of colors is also small. And yeah. And finally, we have given this FPT algorithm parameterized by the maximum degree plus the number of vertices of degree at least k. So as open problem, as two open problems, I would like to mention the most obvious one from the viewpoint of parameterized complexity, which is whether these remaining cases are in fact FPT or W1 hard. And the second problem is, can we exchange the parameterization of our FPT in the parameterization of our FPT algorithm? Can we exchange the maximum degree for the number of colors, which I think might be a nicer result. Okay, that's it. Thank you for your attention.